Okay. Okay, so up to now, we've looked at what is meant by a robot, what comprises a robotic manipulator as a system. We've looked at the homogeneous transformation matrix that you can use to calculate the position of the end effector based on the pose of a robot. Okay, so if you know the joint angles, you know the link lengths, you can use then a forward kinematics approach using the homogeneous equation approach to calculate the final position of the end effector. It's not the most natural way of doing things, and I think I made reference to this at the start in the first lecture. The natural way of doing things, if you think about how you reach, grasp objects, is your brain will work out where the position of the object is in 3D space, and it will set the angles of your joints to reach that object in 3D space. Okay, so up to now you've set the angles, and if you were to go through that process in your mind to reach an object, it would be set the angles up. Are you at the object yet? No. Then you reset the angles. Are you at the object? No. Reset the angles. Are you at the object? No. So the forward kinematics approach isn't the natural way of doing things. Okay, it's useful to give feedback into a control system to check that your inverse kinematics is working right, and the inverse kinematics is probably the more natural way of doing things, where you give your robot a position in space, X, Y, Z. The robot performs the analysis of the algorithm to solve for the joint parameters within the robot, so setting the angles, setting the extension, retraction of the prismatic joints, for example. So that's what we're going to look at today. It's going to start, as we've done before, with simple planar mechanisms. There's a few other things you have to think about when you're solving for the inverse kinematics, though, and I'm going to go through that today. Okay? Okay, so there's a fair bit of preamble up front that will just cover what I've already said. Okay, so what I've drawn there is just a simple planar robot, 3 revolute joints, but it only operates in the plane of the board. Okay, so 3 links, L1, L2, L3, 3 revolute joints, theta 1, theta 2, theta 3, and there's a gripper on the end, and we want to be able to control the position of that gripper within the plane of the board. So for here, our coordinate system is okay, so there's no movement in or out of the board for this. So forward kinematics, hopefully you know by now that we know L1, L2, L3. So these are the link lengths, and we always know those anyway from the geometry of the robot. And these are always fixed, rigid, they're not flexible. But for forward kinematics, we also know the joint variables. Okay, so we pose the robot, we set theta 1, theta 2, theta 3, and that will place our end effector or position of our end effector or the end effector mount point, whichever point at the end of the robot arm we're interested in, at a point in space. So if we know L1, L2, L3, we know theta 1, theta 2, theta 3, we can then directly calculate the position of the end effector. Okay? But as I said, that's not really the natural way of doing things. What we want to be able to say is, given our robot, we understand its work envelope, so we want to pick up an object or manipulate an object, interact with an object within its work envelope. So the work envelope is where the robot can reach. We want to be able to interact with something within that work envelope at a particular point. So we know the position of that thing in the work envelope, and we want to direct our robot to go there. So we want to calculate theta 1, theta 2, theta 3, or D1, D2 if it's a prismatic joint, etc. So for inverse kinematics, we know the desired position of the end effector. Within the robot's workspace. So we call that point P, okay? And given a point P or a desired point P, we need to determine the robot joint parameters, okay? Okay, so put there, given a point P in our base coordinates, so x0, y0, z0 means that's the coordinate system fixed to the base of the robot that never moves. So any object you want to locate within the workspace is always with reference to the fixed base coordinate system. Okay, so given that point P in space that the robot can reach, we need to determine what the joint parameters are for that robot type. So what is the angle of revolution for the revolute joints? What is the extension retraction of the prismatic joints required to reach that point in space? Okay, so that's the more natural approach that we would use when we're automating a process. Okay, so a bit of an example, and this is directly related really to your coursework, is what are the joint variables? So use this method to calculate the joint variables required to pick an object. Pick an object up from a point P, so P1 with reference to our fixed base coordinate system. Okay. So that's what we're looking to do. We've got an inverse problem compared to the forward problem that we've done up to now. Okay. So a couple of caveats there is and don't panic about this statement at the moment. Okay. The forward problem is typically fairly straightforward to solve. You go through a set process, there's a set of rules you follow, and as long as you know what those rules are and that process is, it's fairly straightforward to come up with the right answer. For the inverse problem, you have to come up with a set of equations. Those set of equations will require solving. The complexity of those set of equations will very much depend on the complexity of the robot. And it goes back to something I mentioned previously as well. The more revolute joints that are introduced into your robot manipulator, the more difficult it becomes to solve this problem. Okay? But so in all our configurations, we're only going to look at the first three joints. So that's the three major joints that allow you to position the end effector anywhere in space. For the coursework, you do have to think of the end effector, but it's only an simple numerical extension to the position of where it's mounted. Okay? So you don't have to worry about orientating that end effector to solve the coursework problem. And to do that, we need a set of equations that relate the position of that end effector to the joint variables, or relate the joint variables to the position of that end effector. I think I've already said difficulty. So difficulty of problem is simply related to the robot configuration. So there are two approaches. The inverse problem. Analytic, where we come up with a simple-ish set of relationships that relate the joint variable to the desired position in space. And we're going to use an approach called geometric inspection, where we simply look at the robot and we are able to derive directly the required set of equations. That's okay for simple robotic structures, but when we go to more complex robotic structures, we need to move to more complex algorithms or numerical approaches. Okay. Right, just a few more sentences before I get to the point of all of this. So that's the approach we're going to be using here. It's fairly straightforward. Okay. So using the inverse approach, you'll come up with a set of equations. So if it was for a 3-revolute joint problem, you'd come up with an equation for θ1, an equation for θ2, and an equation for θ3. And you'd set those, you program those into your robot and hope the robot then reaches the point in space you want it to move to. In reality, there's a couple of things you have to think about. One is really outside the scope of this module, because we're only a 10-credit module. Need to be aware of something called singularities, and I'll show a video really to explain what we mean by singularities. Typically with a robot, you want your end effector to move through a defined path. So you constantly adjust your joint parameters to move your arm through that defined path. Now, if you're not aware of this concept of singularities, the robot will perform in a way that you don't want it to, and I'll show that on a video in a second, and we can discuss the implications of that. Okay, and then that's something else we need to be aware of, is you'll come up with a set of equations. They may not generate a unique set of joint parameters to reach the same point in space, and I'll illustrate that in a few moments, but hopefully you've got this loaded up. So this is a 6-axis robot. What it's doing here is just demonstrating where the wrist is, okay? And we're essentially going to be wanting this robot, its end effector, which is, say, the end of the pen tip, to follow a line in space, a continuous smooth line in space. And our inverse kinematic approach will continuously adjust the parameters of the joints to allow that tip of the end effector to follow, or hopefully follow, a smooth line in space. So that's just showing you where the wrist is. Can anybody see what's happening there? So remember what I said, we want the end, the tool tip. So think of that, if that was a spray painter, a laser cutter, or a welder, for example, if you watch the tip as it moves, as the wrist adjusts itself to give it a smooth, continuous path that's programmed into it. See if you can spot what happens.
It starts, it continuously following, it kind of stops, pauses for a second, and
Yeah.
moving.
Yeah. So you want it. So what was happening there is the tooltip was moving along a straight line. It would stop because the robot would have to switch the joint around by, say, plus 180 degrees. It can't do that instantly. It has to take a finite amount of time to do that, and before it can continue moving along that straight line. Okay? So to maintain the straight line, continuous line, it has to basically move the joint through 180 degrees and continue. But whilst it's doing that, there's a pause. So if you think if that was a source of heat, a source of spray paint or something, at that point there would be too much heat. It would probably melt or weld too much metal, deposit too much paint. So that's what we refer to as a singularity. and we're asking the robot to do something and basically change its configuration instantaneously to give us that smooth movement. So now we're looking at the shoulder, which is the joint that's revolving around the base. And you can see it's having to do the same again. You're having this kind of pause happening. And then, is this the final one? Then we have one at the elbow and the set parameters that are being fed to the robot to get it to move to where we want it to go. Simply locked the robot up at that point. I think that's the one anyway. So it wasn't going to do anything else apart from just kind of wobble around because it's been asked to do something it can't do. So that's an example of singularities within a robot system. You can't just accept that the robot will perform what you want it to do once you solve the equations. Right. The link to that will be available on Moodle later on if you want to have a look. So the second thing we do have to consider, and this may come into your coursework, is the potential for our set of equations to have multiple answers. Okay? So multiple solutions. So okay, so this is our very simple single link planar arm robot. What do we do? Okay, so So the forward solution, and we already know how to do this, is px L1 cos theta 1 Okay, so that's just the situation for the forward solution. And so we choose theta 1, and that will determine the position of our point at the end of the robot, pxy. Sorry. So for the forward solution, choosing theta 1 here sets pxy. Okay, so we know that already. We know that's the forward solution. So the inverse problem requires our px, keep the notation. So sets theta 1 sets px, so our x coordinate of our point P, and the y coordinate of our point P. The inverse problem requires px and py up front, and then theta 1 is calculated by solving the inverse problem. So what we need now are equations in theta 1 to give us the inverse solution. So we can rearrange equation 1. Oops. Gives cos theta 1 equals px over L1. Okay, so here on the right hand side we know px, that's our desired point in space. We know L1, that's the fixed link length, and given those parameters we can calculate the angle to give us our point x. Okay, so if our link length is length 1, the point in x that we can reach is either goes from 0, so that's the link is vertically up, so theta 1 is 90 degrees, or it's theta 1 is 0 and the link is horizontal. Okay, so the end of that link would then be at 1. So the position in x that we can reach varies from 0 to 1. So I want to set px, we want px to be at 0.707. There's obviously a reason for that. So anybody with a calculator want to say what the answer to that is? Sorry? 45. is it only 45?
Whatever you
Sorry?
Minus 45.
Yeah, so there are two solutions for that problem, okay? So we might have wanted, and those solutions exist in two different quadrants of our system. So if we go back to the original diagram, we've chosen px to lie along, to be at the position 0.707. So that diagram will do that, for example, if theta 1 is pi over 4, so 45 degrees. Is also a solution, okay? So if we wanted to place our end effector above the y equals 0 axis, it's the positive solution. If we wanted it below, it's the negative solution. How do we determine that when we're kind of carrying out our analysis? Which solution do we pick? So simply using the inverse cosine here causes us problems. Okay, so we would know py as well, but that will give us the same problem. Okay, so if we give a known py, a known px, a known py, we can generate multiple solutions for the same problem. Some will place the robot in the desired position. The other solutions, if we choose the negative ones or the wrong combination, will place our point in a completely undesirable position. So which do we want to use? So I'll come on to the next step in how we overcome that. We'll have a 5-minute or so break, so if you can be back at 5 past, and we will carry on. Okay, so we've got to the point where we have, for a given px and also a given py, we can come up with an equation to calculate the joint parameter. For the single link, it doesn't really matter which one you use, because there's only a single link, there's only one angle. So picking either px or py will give you a result to set the end effector position at the correct point in space, or not. It depends on how your algorithm chooses to solve the equation. As we've just seen, there are two solutions for the inverse cosine, and that's plus and minus. Okay? So the approach to coming up with the inverse kinematic equations that I'm going to use uses a trigonometric approach. Okay, so you're always going to come across cosine and sines. So how do we get around this problem? Okay, so has anybody come across that function before, a tan 2? It's important that it's a tan 2, not just a tan arctan. Okay? It's not often found on calculators. Don't worry about that. You're not going to have to solve if you're asked to do an inverse kinematic problem in an exam, you're not going to have to come up with the exact numerical solution. You'll just need to develop the inverse kinematic equations. Okay? But what will be key in there is using the correct functions within those equations. And one way around the plus minus result from the inverse cosine is to use a tan 2.
Is it like squared or
Just 2.
just 2?
Just 2, yeah. Wait, where? So that function will exist in programming languages, for example. So if you're using MATLAB, C, C++, most other new engineering programming languages will already have that. Okay, and for this, we get a tan 2 is theta equals a tan 2 y over x. So if we know y over x, we can get theta, and theta will always be in the correct quadrant. Okay, so if you use the a tan 2 function with the values of the coordinates you want to hit in, you will always return the answer in the correct quadrant. Okay, so that's what we typically use within a robot system when we're solving for a joint variable given a set of coordinates that we want to hit. But I said I'm not going to ask you within an examination scenario to come up with a numerical solution to the inverse problem. You will just want the correct inverse kinematic equations. So I'm going to do a simple inverse kinematic problem now. So it's back to the 2D 2-link planar arm. We're going to solve the inverse kinematic problem for that. And then I'll lead on to why this one's probably important for a number of things. So we normally start off with this problem because it's simple, although it's not a very realistic, real-world example of a useful robot. But what we're going to do here will be of use for more real-world situations. So we're considering our two-link planar arm, and we're going to consider the system at rest, and at rest it has a certain pose. And for this analysis is the first link will lie along the y equals 0 axis, so along the horizontal axis. There's a revolute joint at the end, and the second link at rest comes back on itself. Okay? So that is with both theta 1 and theta 2. So revolute joint 1, revolute joint 2 set at 0. That's our fixed base coordinate system that's fixed to our first joint, theta 1. And we have link lengths that are equal L1 and L2. Okay, so the way they're set out there in reality is probably going to be not quite as simple as I've drawn it, but for this purposes, that's what our situation at rest is. So we're now going to pose the arm, so we're going to set the arm to a configuration. And this is simply done now to come up with the equations we want to solve the inverse solution, come up with the inverse solution. So we pose the arm, so we can draw it in any other way we want. And so I pose the arm here, so we have theta 1, theta 2, L1, L2. Okay, so that's the situation. So what we want to do now is, for a given px0, y0, we want to come up with an equation for theta 1 and theta 2 that yields, hopefully, a unique result. We could also have drawn this that way as well, and that would allow our manipulator to reach the same point in space, so there's a different set of solutions. If you start that way, you'll come up with a slightly different set of equations. It doesn't really matter, but this way for me is convenient. And what we refer to this as is kind of the elbow up configuration. So the middle joint is your elbow, so it's kind of the elbow up. If we were to have started the other way, our elbow is down, okay? So I think I'll refer to that a bit later on. So we pose the arm, and we want to come up with some equations now that relate our joint variables to our position in space. So what we typically do from this point on is we look for triangles within that geometry that we can come up with trigonometric expressions for the angles contained within them. Okay? So from here we have, there's two triangles that I'm going to focus on. One is formed by the links up here. And the other one, and the first triangle is not very friendly in terms of using, but here can come up with a right angle triangle within our system. So what I want to do now is I've drawn some triangles in. I want to label up some of the attributes of those triangles. So we know the lengths of the links. We know the internal angle. Where's my... Can't find my laser pointer anyway. So okay, we have the internal angle theta 2, and we can label up, there's an angle here between that green line that I've drawn in to form a triangle, and we also have another angle we can draw in here, which is between the horizontal axis and the purple line that I've drawn in to give us that hypotenuse at the right angle triangle. And we can label these alpha 1 and alpha 2, okay? And so what can we say from this point? We can also label this line. So that line is, for the green and purple lines, the same length in both of those situations. So from there we can start to use simple trig to develop some equations from what we can see on that diagram. So the first thing we can come up with is h squared equals px0 squared plus py 0 squared. Okay, so I hope you're all comfortable with that. The next one, we can come up with an expression for alpha 1, and that is knowing, we know, remember, because we said up front the point we want to hit is px0, py0. That is coming back to what we just discussed, a tan 2 py0 over px0. So we've got two equations. What else can we do from there? We can also come up with an expression for alpha 2. So we have a triangle, we know the lengths of the sides, we know angles contained within it, so we can use the law of cosines to come up with an expression for alpha 2. Okay, so that's from the cosine rule, law of cosines. So that's where that equation has come from. And then from there, remember, we're after solutions for a given px0, py0, we're after solutions for theta 1 and theta 2. Okay? So theta 1 in our redrawn diagram, where we've added a couple of other triangles, or we've annotated a couple of other triangles, theta 1 is simply alpha 1 plus alpha 2. And in both of those expressions that we developed earlier, we know everything given px0, py0. and theta 2 again comes from the cosine rule. Okay. Should you need it, the cosine rule will be on the formula sheet of the exam, should you need it. So we still have the problem though, we've got an inverse cosine in there. Which solution do we take? So for this, it really will end up with either that elbow up or elbow down solution, depending on which we pick. So for all intents and purposes, it doesn't really matter for this. We're still going to be in the same, we're still going to hit the same point. So where two solutions will give you the right point in space for you to hit, that's fine, you don't need to worry much about it, but you can come up with a situation where you might have an obstacle in your workplace or in the work envelope. So sometimes you'll have to include that within your whole algorithm. You'll have to have areas programmed in where your manipulator is essentially forbidden to go. Okay, so you'll have to make sure that your manipulator can't impinge or impact any obstacles within your workspace. So you'll have to take further account. There'll be times when multiple solutions won't give you an issue. There'll be times when they do because there are obstacles in the workplace. Okay, and in that situation there are regions within the work envelope that you couldn't reach with that manipulator, for example. So you couldn't get probably below a point just below there very easily, or around the back. So that's where you would introduce that concept of redundant joints that I mentioned some time ago, where we add extra joints within our manipulator to allow it to reach around obstacles. Okay. Okay, so I'm going to go through some examples now of more realistic robotic manipulators and illustrate kind of the full process of looking at a 3D system. So here we have a two-link planar arm. We have one view of it. Any movement of theta 1 and theta 2 changes the picture in the two-dimensional plane of the board. Nothing moves behind, nothing moves out in front, everything happens in the plane of the board. So it's very easy to see what's going on and very easy to come up with a set of equations to represent that. But in the 3D world, things are not as easy. Okay. So the first one we're going to look at is our Cartesian robot. Okay, so this is the simplest one to illustrate. Oop, it's wrong. Okay, so you have to picture this in 3 dimensions. So we have our fixed base down here. We have a vertical upright to this first joint. Then we have the link to the second joint is going directly into the board. And then in the plane of the board, we have another link going to a third prismatic joint. So these joints are all prismatic in this situation. So the first joint moves the whole thing into and out of the board. The second joint moves the whole thing along the plane of the board, and the third joint moves our end effector, point P, vertically up and down. So that's an initial fixed base coordinate system. So Y is positive into the board, okay? So I can label up some other things that we know. So the displacement there from the ground to that first joint is A1. From that first joint to the second is A2 plus D1. And I'll go on to explain what that is in a moment. Okay, so the dimensions A1, A2, A3 and A4 are all fixed. So the height of the first joint off the ground is A1, that's always fixed. A physical real-world joint will always have some dimension that adds a bit of displacement within the system, okay? So the whole thing doesn't retract back to 0, it will retract back to a position that's dependent on the size of the actuator itself. So if the actuator is fully retracted to 0 position, it will still have some physical size that we need to take into account. And that's what A1, A2 and A3 are doing. So you might have a prismatic joint that's 50 centimetres long. It will extend 2 metres, but we always have that fixed initial 50 centimetres to account for if we want to move it to a 0.1 metre away from the start of that joint. So we have it's 50 centimetres initially, and a 50 centimetre extension gives it 1 metre total displacement. Okay. When you come to an exam and you're looking at an inverse kinematic problem, I'm happy that if you were to say having to solve this, you simply say at the beginning A1, A2, A3, A4 are all 0. Okay, so you can kind of remove them from the situation. Keep them in if you want, or you can simply say they're all 0. And that's fine if you want to do that in an exam. But you have to make that point. If they suddenly disappear and you haven't made the stipulation that you're going to consider A1, A2, A3, A4, etc. to be 0, then you could lose a few marks. Okay, so D1, D2 and D3 are the joint variables. So at that point we have all the information we need to come up with a set of equations that will allow us to position our end effector point P anywhere, within the work envelope. Okay? So what do we do here? So we've got 3 unknowns, D1, D2, D3, so we need 3 equations. So we need to come up with an approach to drag 3 equations, each for D1, D2 and D3, out of this system. Okay? So as I said, we've got 3 unknowns. Therefore require 3 equations. For D1, D2 and D3, which are the variables within our system. So there's a process that we go through now that's the same for any 3D configuration. So we visualize the manipulator from the side. What I mean by that is view along view the manipulator along the positive y-axis, and from that view, that removes one of the dimensionalities for us. So that removes any movement in the y direction at that point. Okay? So we view the manipulator along the positive y-axis. And the second step is visualize from above. Okay, so we're looking downwards along the x-axis. And again, that will give us a view that's removed one of the dimensions, because we won't be able to see any movement in that z-axis, only in x and y. And what we do is we visualize from the side along our y-axis, and we draw out what we can see. Visualize from above down through the z-axis, and again, we draw what we can see. Okay, so what I'm doing, that's my dodgy looking eye, looking along the positive y direction, and we're going to draw out what we can see if we were looking directly along that axis. So we can see joint 1 that's displaced from the ground. We can see joint 3. But we can't see joint 2, because if we're looking along that axis, it's hidden behind joint 1. Okay, so then we can draw or label up what we know. So we know that's A1. We know that is A3 plus D2. And we know that that was A4 plus D3. They're the only two axes we can see. And this point at x0, y0 is our desired point, so we also know that, okay? So in that diagram there, we know A1, A2, A1, A3, A4, because they're fixed mechanical displacements. We could have set those to 0, as I said, if it was an exam situation. And we also know Px0, Py0 and Pz0, because that's our given position in space that we want to reach. So from that view, what we do then is we try to extract some equations for some of the unknowns. Okay, so we're left with a 2D problem. So movement of joint 1 will give movement in the x0 direction, and then movement of joint 3 will give movement in the z direction. None of those joints affect any movement in the y direction, so we've removed that dimensionality. And then we can use that to write out any equations that might apply. So what can we say from that? We're given px0, py0 and pz0. So from here we can write px0 equals, anybody want to suggest?
A3 plus a D2.
Yeah. Okay, and that's our first equation, which we then need to rearrange, because remember we're after the joint variable. Okay, and that's our first equation for D2. Okay, so it's simple as that. And all we look again and say, what else can we come up with from that view? So we come up with px. Can we come up with anything else? Can we come up with anything else?
PZ.
Yeah. Equals. Crack on. And again, we just rearrange for D3. Okay, so we've got two equations for that. We've got one for px0, one for pz0. That's all we can do from that point. So we then take the other view. So we've looked along the y-axis. Now we're going to look from above. So we're going to look down along in the negative direction along the z-axis. And again, we're going to redraw what we can see. So here we can see all three joints. So joint 1, joint 2, and joint 3. Label up what we know. Okay? So that's what we know from that view. So now we need one more equation. We need an equation for our, which parameter? For D1, which is the displacements of that first joint. Now remember from the other view, that was displacing into the board, so we couldn't see any movement there. So we want an equation for D1, which can simply be given from, anyone?
PY minus A2.
One step ahead, so that's Py equals A2 plus D1. Therefore, D1 equals Py minus A2. That is our third equation, and that's all we need then to solve the inverse kinematic problem for any given point in space. So we give a point in space, Px0, y0, z0. We have three equations to give us all the relevant displacements that we need to put us in that position. Okay, so the Cartesian robot here is a very simple illustration of that approach. You won't get that in an exam, okay? You'll get something slightly more tricky. But just a bit of a spoiler for the next session, we're going to look at a SCARA robot configuration. And an articulated robot configuration. Don't worry too much about what I'm scribbling down here. This will all be repeated next week anyway, this bit. Okay, so we're going to look at those two configurations in the next session. They're more complex to analyse than what we've done so far, but if you look at the side view from one aspect of the articulated system on the bottom, here and here is a two-link planar arm, and we've already done some of that work. If you look at the SCARA from above, it's also a two-link planar arm from that above view. Okay, so we've already done a fair bit of the work in the 2D planar arm there. So I'll just develop those into the full 3D solutions next week. Okay? Okay, thank you very much.